Great, thank you. Yeah, so I'm Tyler Nighswander from Theori. I think a lot of teams are going to talk about a lot of different stuff, but I thought this would be the most fun, and our architecture is a little bit interesting, so I thought maybe people would enjoy hearing a little bit about it. So hopefully most of you kind of get the idea behind this AIxCC thing, right? You want to make some patches, you want to make some POV input things, you get some weird magical LLMs. Great, sounds wonderful. You can use other stuff, right? You can use anything you want, but really the whole idea here is we should be using AI because it's the cool hype thing. So patching, honestly, I think most people get this idea today, right? This was maybe interesting last year, like 2024. In 2025, everyone knows what Claude Code is or Codex or whatever. Let's not talk about that. So patching agent for those things, Claude Code, Codex, most of them have a single tool or some kind of very simple tools based primarily around a Unix shell, right? Unix shells are wonderful. They can do anything you want. That makes them terrible. You don't want to do anything you want with an LLM because LLMs make mistakes all the time. So our approach is a little bit different. We basically have kind of a few different categories of tools available to our LLM agent. These are further broken down. So actually, we have this set of tools. So our patching agent can read code, it can make changes, and it can test patches. And if you've ever used anything like this, test patches is a little bit scary as a tool. Actually, yes, it can test the patches if it wants, but we also automatically test the patches, right? You want to do all of this stuff automatically if you can. And for reading source code, so we don't do the thing that some tools do where it's like, I'm going to read a file or I'm going to read a few lines of a file. We prefer instead to do static analysis, and we'll have something like, our agent wants to read the definition of foobar. I'm going to run every tool that I have in my toolbox to find it, the proper definition of foobar, and I will give it to it. Right? I'm not going to let it try to browse the code base because that's a hard problem, and I can solve that statically. We also have this weird thing on the side, source question. So source question is actually a sub-agent. So we'll talk about that a little bit more later, but the basic idea is if you have a more complicated question, right? I'm not asking to read definition. I'm asking, what's the maximum size of this argument in the function? Reading and understanding that complex query takes a lot of context tokens. It takes a lot of reasoning. It's better if we can shove that off somewhere else. So basically, the idea here is just that sub-agents can keep the context window clean. There's a couple things about this, right? So the first is the number of tokens that you're using, right? Agents or LLMs have a fixed token size. But even if they have a token size, like on the box advertised at like 1 million tokens, that's not really an effective token limit. Realistically, once you get past like 32 or 64K tokens, the performance degrades significantly. Hallucinations, just repeated outputs, a bunch of stuff. They also just get distracted, right? If you have a bunch of source code in your context, they're going to attend to all the different pieces of that source code and get really confused about what's going on. So, if we want to do one of these kind of more complex queries, we can do this. And it also naturally compresses the context, right? Trying to answer this question, maybe we generate tens of thousands of tokens trying to read all the relevant source code, but the output is very small, right? Maybe that's only 12 tokens to give you the response. So this naturally compresses the context, which is a great benefit. OK, so we have a patching agent that produces patches. Problem solved, right? Well, there's no human in the loop. This is AIxCC. We don't get humans. So what do we feed to our patching agent? I am very smart. Bug reports. I will get bug reports. How do we get bug reports? Static analysis, right? So patching agent maybe runs $5, right? We can run a few different ones in parallel. We gotta test a few things. Bug reports, great. Lots of false positives, 10,000 results. It's going to get expensive real fast, right? That's not going to work. We can't run $50,000 of this crap. So what do we do? What if instead we filter the reports, right? We get bug reports and we do something with them so we don't have 10,000 shitty reports. So how do we do that, right? It's not obvious. And this is actually a really complicated and interesting problem. So our approach is kind of a multi-tiered pipeline. So the first is we run an LLM classifier. So you're probably familiar with a classifier in general, right? You have some sort of multi-choice output. In our case, it's a binary output, yes or no. Is this a real bug? You might think about this, and if you think about this for more than 2 seconds, you realize this is an impossible problem, right? You can't look at like a small function in a bug report and say that it's a real bug report. But maybe you can use your intuition. You can guess. You can get a basic idea. So what we do is we don't just get a binary out of this. We can use the probabilities that the LLM is going to generate, right? LLMs sample, they generate a probability vector. So we can sample from that and get a analog between 0 and 1. And then we can use this to score. So this isn't necessarily a filter. This is more of a priority queue. And the benefit here is it's insanely cheap, right? This is like a cent or a tenth of a cent to run. So if we have 10,000 reports, no problem. But there is a problem, which is that there's a lot of false positives still, right? We get the top 10%. We had 10,000 reports. That's still 1,000 reports. And so what we do next is we run an LLM agent. The LLM agent takes what we consider to be a reasonable report, starting from the top of the most, the highest priority, works its way down. So the idea here is this is a little bit more expensive, right? This is, let's say, 50 cents a report. Still can't run 50 cents on 10,000 reports, but I can run 50 cents on 1,000 reports, right? So what we do is at each stage of this pipeline, we remove a little bit of the results. We get fewer and fewer results, and now we can spend more and more resources as we move through this pipeline. So the nice thing is you can also tune these, right? Like we tune them for what we thought was reasonable in AIxCC. In the real world, if you want to tune them to your own usage, you can. So it's a nice approach. Great. We have a wonderful pipeline. We get bug reports. We filter them. We patch them. We make patches. We have POVs that are not being generated because that's not what this is doing. So, OK, how are we making POVs, right? How do we actually make inputs to trigger these bugs and demonstrate that this is a real bug? There's the obvious answer, which is fuzzing. Everyone probably knows fuzzing. You run some random inputs. That's great. I don't have a problem with fuzzing. I love fuzzing. Where are the LLMs, right? I thought that was the whole thing. We're in 2025. We got to use LLMs everywhere. That's the whole thing. So just taking a step back, though, how do we even integrate this, right? Our patching takes in bug reports. It doesn't take in binary inputs that trigger a crash. That's not so bad, right? All we got to do is just triage the bugs. If we triage the bugs and we generate a human, natural language, whatever, then we have an input that we can trigger. So this is an agent, once again, outputs a root cause, at a source browsing, it looks at a stack trace, whatever. So can we give that to our patching agent? Well, we still have some problems here. So one is that these are two independent pipelines. The other is just that fuzzing in general produces duplicate results all over the place, right? If you were fuzzing, you're going to keep doing this again and again, and you're going to patch. We decided $5 a patch. Great. Our fuzzing is just going to produce a bunch of duplicate bugs, and it's going to suck. So what we need to do instead is this more complicated thing where we're deduplicating the bugs. The nice thing here is that our agent is outputting a root cause. We have natural language descriptions for every bug in this pipeline, right? Every bug that passed through this left-hand side has a natural language description because it's a bug report. And now we get this triage agent that's producing a bug report. We can deduplicate this. Once again, we use an LLM classifier. The LLM classifier says, OK, I have a multiple choice question. There are 10 bugs that I have determined are relevant. You gave me a new bug. Does this English description match any of these other descriptions? That's a multiple choice question, so we can use a classifier. OK, great. But we didn't really do anything with the LLMs for these bugs, right? We still just used fuzzing, and that is not very satisfying. And we had decided that these bugs on the left-hand side were accurate enough that we're willing to patch them and spend dollars, like real dollars, to patch them. Why aren't we making POVs for these, right? We're just leaving stuff on the table, and that feels bad. So let's talk about LLM POV generation. This is a pretty complicated problem for a number of reasons, and is way beyond the scope of what I can fit into here. But I think there are two main problems that we've identified with why this is difficult. The first is that harnesses are a real pain, right? So if you're fuzzing something, you need a harness to say how I'm going to get my input into the target program. Part of this is that for some projects, you might have 30 harnesses. Your LLM needs to figure out which is the relevant harness. That's already a non-trivial problem. The second is that harnesses are encoders, right? They're taking some sort of data and producing binary blobs on disk. That's one packed blob of data. This could be protobuf. It could be TLV data. It could be compressed. It could be really anything, because whoever wrote the fuzzer gets to decide what they want to do. The second problem is context windows are limited. So we talked about before, even a large context window can degrade quickly. So for the harnesses, what we do, well, we're going all in on LLMs, so we'll make another LLM agent. So the LLM agent here is responsible for what we call harness encoder agent. So the idea here is, what if we had an agent doesn't know anything about POVs? It doesn't have bug reports. All it knows is I have a harness, and I want to make something that serializes to the same kind of natural serialization structure that a harness is using, right? A harness produces binary data on disk. That's a serialization format. Coding is a thing LLMs are great at. We'll ask the LLM to produce a Python library which encodes how this encoder works and gives us semantically relevant arguments. And then for this context window thing, we talked about this a little bit before, but we can use sub-agents, right? Sub-agents break up these big tasks into little tasks, and that naturally has a compression, which really helps keep our context window clean and small. Great. Now we got this little pipeline, POV agent. Obviously, the POV agent goes to the POVs. Maybe. That doesn't quite work. So the problem here is that LLMs love to do whatever they love to do. So what if we told it to exploit a bug and it exploited the wrong bug? That totally happens. It's kind of silly, but maybe you gave it a really deep, complex bug, and it couldn't figure it out. And along the way, it found a really stupid buffer overflow or something. Great. Luckily, we already have a pathway for this. Pass it to the triage agent. Integrates with our whole pipeline. So this is really cool. I think this is kind of the fundamental thing that we did, and we did differently from a lot of teams, which is that everything inside of this green box is an LLM or LLM-based, right? So we can turn off fuzzing. In fact, most of the bugs that our system finds are not found through fuzzing. It's something like 75% are not found through fuzzing. And it works. Everything works. And that's really cool because when GPT-5 comes out yesterday, we can plug that in and see how it does, and it improves. So great, but now we have this stuff outside the box. And like, why aren't we using LLMs for this stuff outside the box, right? Why are we restricting everything inside the box? So there's some easy things to do. The first, what if we can use our POV agent to help out our fuzzing, right? If we are producing a POV, right, we're trying to crash the program. We're producing, hopefully, deep inputs, which are accessing a lot of the kind of interesting parts of the code. So if we're doing this, even if it didn't crash the program, right, even if it wasn't a valid POV for scoring or for like whatever purposes, it might be a really good seed for fuzzing. And so we're naturally producing these fuzzing seeds along the way. So this is nice, but what if there's actually nothing flowing that direction, right? Like maybe our fuzzing wants to be working, maybe our static analysis failed, maybe our static analysis is bad, maybe we just couldn't find any bugs, who knows? So what if we just have another thing, right? A fuzz helper agent. A lot of people, if you think about like the CyberGrand challenge, a lot of folks, what we did is we would use symbolic execution or something. The symbolic executor can assist the fuzzing by generating inputs when the fuzzing is stuck. So what do we actually need, right? Like, this can't just be a one-directional thing. This needs to be bi-directional because it needs to know how to help the fuzzer. So now we need to add something like a coverage database. So this isn't too bad, right? This is a known engineering thing, not a research thing. But basically what we can do is we can take all of the stuff that we've done through fuzzing, we can run that through a coverage database, collect the coverage. Now we can do static analysis to say, hey, there's a bunch of coverage left on the table, right? If you ever called foobar, you would have a really interesting time fuzzing that, and you've never called foobar. So as my fuzz helper agent, I'm gonna make that happen. Well, now we have this wonderful coverage database, and all we're doing is fuzzing. Why don't we give that to the POV agent too? So there's a couple ways that this can work. Primarily, when we launch our POV agent, we don't use this pipeline at all. But if our POV agent runs and we have a useful input, and it has failed a couple, like the POV agent failed a couple times, then we'll start using additional inputs, right? So we'll say, hey, you were trying to exploit foobar. You couldn't reach foobar because it's really complicated and you're an LLM and that you're having a hard time. Well, we can take the foobar input that we got through fuzzing, and we can give that back to the POV agent and say, hey, can you make a POV if you already start from this function, right? That gives it a huge boost and makes its job a lot easier. Cool. So the other thing here, we talked about this. Now we have an agent. Our fuzzing is going directly into an agent. Agents are dollars. Agents aren't cents. This isn't cheap. This isn't too bad. Kind of this a little easy dedupe thing, right? You can do stack hashes, like figure out where it crashed, what it looked like, what instruction pointer. That's not too bad. There's another thing, though. If we take our patches, we can pipe that all the way through as well, right? So if you imagine that this pipeline has already patched a bug, if that patch also fixes an input that you found through fuzzing, well, naturally, you have already fixed that bug. We already have a root cause for the bug because everything on this left-hand side already has a root cause associated with it. So we're all good, right? We can just use that directly to dedupe our bugs separately from using stack hashes or these other techniques. So we use them in parallel, but that just helps to reduce the work that we have to pass to an agent, which, again, more expensive. Well, we need our patching agent to be doing a good job. So the other thing is we can feed our POVs into it. Obviously, when it started, we might have given it a POV and said, like, here's the crash you're trying to work on. But again, we also have this really nice thing where every POV, every patch is associated with a root cause vulnerability. So we can say, hey, my patching agent said that it patched these, whatever, this root cause. I have 15 POVs that I've generated through fuzzing, through whatever, that are all minimized or deduplicated to the same root cause. I will pass that and make sure that my patch patches all of them. Otherwise, I'm going to restart it. OK. So there's a lot of details that we're leaving out here, right? One of them is like, what the heck do these arrows mean, right? Like, what does it mean to pass coverage thingy into POV agent or like POV into patch agent? Like, we already said that doesn't work. So what we do here is we have a decoder. So this is analogous to our encoder that we use. So much like we can produce an encoder for a harness, we can produce a decoder for a harness, right? It's a serialization format at its core. So we can produce an encoder and a decoder. So what we do here is we do the same thing. We get the binary data that we use from our fuzzing input, and we decode it into semantically meaningful data. This is nice because really, like, what does it mean to pass binary data to an LLM? Like, yeah, you can hex encode it, but even if you hex encode it, is the LLM going to understand it, right? Like, are the token boundaries that the LLM is going to use, is that going to match up with bytes? Are you going to have like 3 nibbles for a token? That's going to be really confusing. Even if you don't have 3 nibbles for a token, if you have like a 4-byte length field and then a 2-byte tag, you don't want those to be like just bytes. You want those to be semantically meaningful things, right? But we can create a decoder, much like we created an encoder, and feed that decoded value into the LLM agents, and it can understand this a lot better. Once again, we get to just use an LLM agent for this. We can test it the same way that we were testing our encoder. This time we run it against all the fuzzing seeds or any seed we have, make sure it doesn't crash or whatever. OK. This is getting a little bit unruly, but you think you get the basic idea that we have a lot of these kind of components. They're all talking to each other. So now we got to implement this wonderful, elegant architecture. This is still a high-level diagram, right? Like, there's a lot going on that we can't talk about. Extra classifiers to make sure we're not wasting time, extra agents, extra everything. So when we started this in 2024, there's also like MCP was not a thing. A lot of these techniques people have been working on did not exist. This is all written basically kind of fairly bare bones. So we have some basic things, right? Like we have a queuing system. If you think about this, this is like a pipeline. You start with a thing finishes, you move it into a queue. Each of those components is kind of like a reader writer from a queue or whatever. So we can have this queuing system, but at its core, we actually have a single Python process for all of this, which is a little bit wild, in my opinion. So we have to make sure everything's asynchronous. Luckily, most of our time is spent waiting for LLM completions. So we can just spin up a bunch of stuff. We will actually run literally thousands of agents in parallel, assuming our system's not falling over. And we'll run thousands of agents in parallel, which is OK in a single Python process if it's written properly. For the heavier work, right, if we want to run fuzzing, if we need to gather coverage, we can run that in a Docker on a remote host. But we don't really have a really complicated distributed architecture here. We're not using Kubernetes. It's a pretty simple, straightforward system. So just trying to monitor, like you can imagine that architecture is already complicated. And now I'm talking about thousands of agents. Like the telemetry, like trying to understand what it's doing, trying to understand why it's spending $3,000 in an hour, it gets a little bit complicated. So we have a bunch of graphs and a bunch of this other stuff. It's hard. So yeah, I know this is a short talk. We don't have a lot of time, but I guess part of the thing that I really think people should take away is that LLMs can just do a lot of things. I think a lot of people take these traditional approaches and they say, like, how can an LLM help me do this thing I was doing 5 years ago? And I think we should really be transitioning into, like, what can an LLM do today, right? There's things that LLMs can just do that we couldn't even think about. And we're not using LLMs to their full potential. I think that realistically, if all the providers just stopped, right? They turned off all their GPUs and were like, we're done. We're not training any more models. I think there's still like 2 years or more of stuff to squeeze out of these models, mostly by running like more scaffolding, right? Like we have a lot of tools and a lot of static analysis and a lot of things designed to make, ergonomics for LLMs. And I think that's really where a lot of the stuff left happens. And these systems can find real bugs. I guess some of this was after I wrote these slides, but we've reported a few dozen 0 days found with the system not through fuzzing. And this includes heavily fuzzed things. We had some exploitable out-of-bounds heap writes in SQLite that were fixed on Monday. And you would never fuzz them. Wonderful. So this QR code, we actually have a lot of things, including agent trajectories. The agent trajectories for those SQLite bugs, now that they're patched, are actually in there. So you can look at those and try to imagine what it would take for a fuzzer to generate like a zip file that is hex encoded, that is used in a select statement with the zip module in SQLite. No, a fuzzer's not going to find that. So there's all our stuff's up there. There's a link to this thing also on the DARPA website, and if you stop by our booth, I got like the same QR code there. Yeah, I don't think I'm supposed to take questions up here, but I will be around here, so feel free to talk to me. Or if no one stops me, you can do questions. I don't really know. There's no one here, so thank you.